Hopefully you can see my intro slide right now. So I will first be talking about a little bit about the theory and the challenges we have with many objective optimization. And then Marcus will take over. So essentially we can face different type of optimization problems, and there are very many different classifications and categories and so on that you can do. But essentially, if we focus on the number of objectives, we can have a single objective optimization problems where you only optimize for one entity or characteristics or something. And those problems are the ones that are easiest to solve, generally speaking, for optimization algorithms, and it's also easy to plot and understand. To the left, you have just a contour plot showing the function value curves for a single objective function. Then when we have multi-objective optimization, we have two or more objectives that we need to consider in our optimization. And this means that what we probably get will be a Pareto front where we have many solutions that are optimal in a mathematical sense. And as long as we have two objectives, it's still quite easy to understand and interpret and such things. So in the middle figure, we have a trade-off between a volume and stress in a truss system, for example. But then as we increase the number of objectives, so we have more than 4, then it will be much more complex both to solve the problem, to identify the Pareto front, and then afterwards to understand and plot the trade-offs and the different designs will be much harder the more objectives we have. And this is called the curse of dimensionality. So generally speaking, the more objectives we include in our optimization, the more difficult the optimization problem will be to solve. And we probably also need more function evaluations to get as much data about the Pareto front as possible. And this means that we'll have longer wall clock time where we wait for the optimization to finish. And also an increasing difficulty in visualization and understanding of the trade-offs, and it will be more difficult to select the design that we would like to recommend. So the optimization then, or the optimization algorithms, their main task is usually to find the Pareto optimal solutions, unless you have included some information regarding what you are looking for. So you have made a weighting regarding how much you like each objective yourselves beforehand. So the optimization wants to find the Pareto optimal solutions, and for that we need two things. First, we need to tell the computer how it should rank all designs, whether design A is better than B. That is what I will talk about next. But we also need to have, if we use evolutionary algorithms, for example, or other population-based algorithms, we need at least one individual for each objective to perform optimization. And that is because we need at least one individual to explore and try to minimize F1, and another one to minimize F2, and so on. And then we would still not get any information about what happens when both F1 and F2 should be quite small. So we need at least one individual for each objective, and this means that the more objectives we have, the larger population we need to have as well. So is design A better than design B? This is something that is crucial for the optimization algorithms to know whether a design is good or bad, and to rank the designs. And first and foremost, almost all multi-objective optimization algorithms will first try to rank all the points according to Pareto ranks. So essentially all Pareto optimal points will have rank number 1. And then we can remove those, and then we take a look at the rest of the points, and we see that now these are Pareto optimal. So then those points will be of Pareto rank 2, and then we have Pareto rank 3 and 4 and so on. So the difference then is how the different optimization algorithms should rank the designs of the same rank. So in this case, we have 4 different points of Pareto rank 1. Let's say that we only would like 3 points to be carried over to the next iteration or generation. Then we need to determine which of these 4 points that we do not want to have. And how to do that operation is something that differs between different optimization algorithms. So when the algorithm considers this, generally speaking, we would like to have our Pareto front at the end of optimization to show convergence, meaning that all presented designs should be Pareto optimal. We also want to have a large spread, meaning that we want to have the best values for F1, F2, and so on present in our Pareto front. And we would also like the designs that we have to be as evenly distributed as possible. So I've stolen this figure from a research paper, and in the figure to the left, you have an example of quite good distribution between these 5 points. And in the picture to the right, or figure to the right, you have an example of a good spread. So ideally, we would probably like to have something where we have this point and this point, which corresponds to the optimal F1 and F2 values. And then, so that means that we have a good spread, and then we would like to have the rest of the points evenly distributed somewhat. So one of the most famous optimization algorithms for multi-objective optimization is the non-dominated sorting genetic algorithm 2, developed by Deb. And to rank the different designs in the same Pareto rank or of the same Pareto rank, they suggested to maximize the distance to the closest Pareto designs. So essentially, they see it as the contribution from this point corresponds to an imaginary box. And the larger this box is, the more important this point is. But they also would like the best design for each of the objectives to be present. So the first or the highest ranks will be this and this point, and then it will try to find the points that have the largest crowding distance, meaning the distance to the closest Pareto points. So if we take a simple numerical example, we have 8 points in this figure. Then it would rank this point and this point best, because they have the best F1 and F2 value for this minimization problem. And then we need to calculate the crowding distance for the rest of the points. The crowding distance will be set to infinity because these do not have any points that have lower F1 or F2 value, respectively. So in this case, point number 2 will have a square that looks something like this. And that is much larger than the other ones, apart from perhaps the one we have here for point number 3. So in my example here, point number 2 will have rank 3, and then point number 3 will have rank 4 and so on. And point number 1, 2, 3, 4 in the middle here, this will have a very small box or crowding distance, which means that this should be the worst point, and it also is. So depending on how many designs we would like, we would first take point number 1 and 8, and then we'll take point number 2, 3, and so on, and we would not select point number 4 unless we really want to have all points from this Pareto rank. Then Deb tried to improve the NSGA 2 and launched a new version called NSGA 3. And in this case, he tried to get an evenly spread by adding reference points evenly along the current Pareto front. So still, the designs at extreme points will be ranked the highest. And then he creates an imaginary reference plane between these optimal designs, and then he specifies how many designs he would like to have, and will then create reference lines so that they are evenly spread. I hope that the next slide will show this. Pretty cool. Yeah, so if we take this example figure, then we have these as the ones with highest ranks. They have the lowest F1 and F2 value. And then we create a reference plane between those. And from that, we can take or create a reference line that is normal to this plane. And then we say that, okay, we would like to have 2 points or reference points between our 2 best points. So what we do then is that we copy the reference line so that they go through the reference points that we have. And now we would like to take the points that are closest to these target lines as the ones that have the second highest rank. So in this example, these 2 points would be ranked as point number 3 and 4, because they are the ones lying closest to any of the target lines. So there are more optimization algorithms out there. For example, they can use the hypervolume criteria or inverse generational distances and so on to converge. But regardless of what optimization algorithm you choose, when you set up your problem, you should know that the more objectives you choose to include in the optimization, the more difficult it will be for a computer to solve. So it will take you a longer time to get a good result. And in the end, you probably will have a much harder time to visualize the data and understand trade-offs and select a design. However, for me personally, I still like to have quite many objectives and then manipulate the database myself after the optimization, but that is just my personal opinion. So that was it from me.
Thank you very much, Johan. Yeah, maybe I will just try to continue here, and then yeah, and please feel free to interrupt with questions at any time.
Can I ask a question?
Yes.
Yes. So I was curious because, you know, personally, my favorite is a spider chart when you have a lot of objectives and a complex problem and want to make a decision on which design do I really want. What's your opinion on spider charts versus other ways to visualize?
I would say that my boring answer is that I prefer a spider chart or the parallel coordinate chart myself, if I would like to visualize this.
Okay, thanks.
Otherwise, I would try to add several objectives together into one objective. So I could, if I have 3 measures for performance and 1 for cost, for example, I could try to add my performance objectives into one measure and plot that versus the cost. So I try to get fewer entities to show. But otherwise, I would say that I would probably use a spider chart or a parallel coordinate chart to explore data.
Okay, thanks.
All right, thanks. Yeah, before I show the example, I just want to mention 2 things, 2 enhancement in the latest release of HEEDS, and one of them is that the multi and many objective Sherpa algorithm now for handling more than two objectives has been improved, and it also now incorporates state-of-the-art research, including the NSGA3, as Johan talked about earlier. And I will just show you here an example where this has been benchmarked on a 3-objective problem. I will show you soon how that has been done. Here you can see how the search pattern looks like for these 3 objectives between the old and the new version. So what you essentially get is better design diversity and a better Pareto front coverage. And of course, you can use a lot of different criteria when you evaluate different optimization algorithms. The one used here is the hypervolume, and in 2 dimensions, that would be the area that is incorporated or with the members along the Pareto front, as well as the vector of the worst objective here in F1 and the worst objective in F2 and their intersection point W. So then you can clearly see on this problem with 3, the crashworthiness problem with 3 objectives, the hypervolume is larger for the new multi-objective Sherpa algorithm. There's also been, speaking of how to evaluate and look at all the data to make good decisions, there has been improvement to easier see sort of the progression of the whole Pareto front during the optimization study. So here you can see how it's showing all the ranked and the unranked designs during the study. All right, now I will show you an example of actual fan redesign. We have 2 competing objectives. One is to minimize the power requirement. The other one is to improve the mass flow rate. And I think that in general, when you're working on problems like this, you need to go on your intuition when you start to evaluate different objectives here and see if they are competing or not. Because I think that if they are not competing and you use this multi or many objective approach, it will converge into a sort of a single point and not the whole Pareto front. So that's one thing to take into consideration to really make sure that they are competing. And the other one is also how to, for how long do you need to run the problem here? And I think that using Sherpa in general for a single objective problem, some sort of rough rule of thumb would be like for smaller problems, like 3 to maybe 10 variables, you should use at least 10 to, or maybe more like 20 times the number of design variables. That amount of, so let's say you have 10 variables, you should use like 200 evaluations. But I think that if you start to include more objectives, you can multiply that with the number of objectives you also So incorporating, so let's say you go for 2 objectives, that would be 400 evaluations. Maybe Johan can share some I don't know, theory on that. All right, so let's take a look at the different type of variables we have in this problem. N was the number of blades here, and you can see how all these different design variables affect the design of the fan. All right, so that's how the CAD model has been parameterized and how the different design variables affect the design. Here's just examples of how different designs can look like. And then, of course, we need to automate the meshing process also here. So that has also been done. And using star CCM for the CFD calculations. And here you can also see how this Pareto front is progressing. And Sherpa is working on the task. So I just here want to show you, if we zoom in on this lower part here of the Pareto front, you can see that we can find the signs here where we can, the baseline is there. And here we can see how we can go to a different design that keeps the mass flow, but has a much lower power requirement. Yeah, and here I will just want to show you how you can investigate very neatly in HEEDS different designs along the Pareto front if you also use visualization for all your different designs. All right. I don't know, Johan, maybe you can share something about how when working with the genetic algorithm, at least how any rules of thumbs or a theory on how many evaluations you need.
Yeah, sure. I would say that the opinions differ a bit between different research and so on. So there are no like clear-cut guideline that this is the one you should follow. For me, I would probably go with trying to estimate how long one design will take to evaluate with optimization software, and then try to see how much computational budget I have.
Yeah.
So essentially, I would try to see that, okay, how many evaluations can I afford to conduct? So I begin in that end, and then if I want to, let's say that I can afford 2,400 evaluations or something, then I need to see, okay, how much or how large should my population be, and how many generations, if you take MSD 3 or 2, for example, can I use? And and generally speaking, people use more generations than individuals in the population, because the more generations you have, the larger the chance you have that the optimization has converged, while a large number of individuals means that you have more individuals that can search for information, so you can cover the Pareto font better and also explore larger parts of the design space. So for single objective optimization, for me personally, I usually try to have 50% more generations than individuals. So in my example, I would have 40 individuals in my population and then 60 generations, and then get my 2,400 evaluations. For multi-objective optimization, then I want to have more individuals in my population, especially when I have many objectives, so I can cover my Pareto front fairly well. So, I mean, the minimum requirement is that I have more individuals than objectives. But apart from that, I will probably go with a 50-50 split between individuals in the population and generations. So then I would probably go with like 50 individuals in the population and then 50 generations. So I get 2,500 designs. Of course, if you have parallelization capabilities, then this will not be much of an issue, since you can run all individuals in one population at the same time. So you only have to wait for the number of generations that you specify.
Yeah, exactly. Yeah, that's good. But I like your ideas also, or your view on things. Like, I mean, many times when it comes to the practical situation, you have like time constraints, project and you know how long your simulation models is taking and things like that. So you start off from that point, and I think that's the way of working at HEEDS, that you go to the table with your sort of budget, and then Sherpa will make the most out of it. But it's also interesting that you mentioned the parallelization. I mean, that's also something that you can take advantage of in HEEDS, and in those situations when that is possible, like it is in this situation. All right. Any other questions or comments or? I was just thinking, Roberto, are you here with us?
Yes, Marcus.
Hi, Roberto.
Hi, everyone.
Hi, how are you doing?
Very happy to join this call and to see interest in multi-objective optimization. It is, as you know, a challenge that is coming more and more in our daily practice because of the many conflicting objectives that we need to cope with when doing engineering design. So happy that we can share more about the differences between single, multi, and many objective optimization. I enjoyed very much the slides that the professor shared, and I think it's. I would like also to bring a little bit of some good news, I will say, in this regards, not only for what you shared as an announcement that we did in HEEDS in 2304, so in the past release, by including the logic of NSGA3 in the multi-objective Sherpa, but also for some capabilities that we are preparing to launch, I will say, in few weeks with the new 2310 release of HEEDS. But before going to that, I would like maybe to ask the audience a little bit of an open question to hear how many are doing multi or many objective optimization, if it is a common case, if it is something that is now starting, or maybe they are doing it already since years. How many of you have already used multi-objective or many objective optimizations?
This is Johnny here. I can comment in general what I see in the industry now. The automotive industry is that the optimization challenges are really complex, and there is a deadline. So what we really see is that the power of HEEDS and how it helps stimulate collaboration between engineers and generating ideas, even if your study had too short of time to really come up with the final solution. You get a lot of knowledge. So I guess my point here is that many objective is the very common situation, but how we visualize it, it's like very different. In many cases, just simple spider charts, but many objectives is very common.
Yeah, I guess that it's a very good comment that you can consume these results if you have a good way to visualize it, so that there can be more interest or more challenges that can be tackled if you have a good way to interpret the results, that you have a good visualization, whether it is a spider chart or parallel plot, a parallel coordinate, then it has to tell you where are the optimal configurations that you can eventually choose. It should, in a way, support your decisions in complex environments like the ones that you are mentioning. For this purpose, I think that we have some interesting new things that we are about to launch in the next release of HEEDS that you pointed out, Johnny, a very interesting challenge that is also coming up more often from the product management. We hear it more and more, that there is a fixed time budget. And often, whether it is 10 days or a month, this is the amount of time that an engineer or a designer has available to do the work. So what if we can provide an approach or a technique so that we can make better use of this time available? For example, we can either get an optimal or a Pareto front in less time, or maybe get a better Pareto front in the same time. This could be giving some advantages in finding out configurations, but also reusing time and getting an extra opportunity to do more, to further investigate certain configurations. If I can do, if I have a month and in the past I used to have this amount of time to do my work, and now I can complete my work in 22 days instead of 30. Then I can use this extra week or more to do further investigations on the best configurations. I think that what is coming out of the conversation before is that the Pareto front is a set of combinations of optimal configurations, and that all of them have some optimality characteristic with inherent to the points. But which one to choose, it depends on considerations that are maybe not included in the optimization problem themselves. Usually these objectives are competing with each other, like cost and weight in an aircraft or in other configurations. You have conflicting objectives. These objectives need a trade-off, need some way to determine what are the optimal combinations, but which combination to choose is hard. So if I have more time to find my Pareto front and then to make an assessment on the best candidate that I find, then I can pick the right one with more confidence, with more understanding of the design choice that I'm making, right? Marcus, I don't know if you have other slides that you would like to share, but I can maybe give a very brief, super quick intro to this new technology that we are about to launch, if there are no other questions specifically on the multi-objective and many objective optimization that has been presented today.
Yes, please do. I don't have any more slides, so I will give the screen to you now. Thank you.
All right. So I don't want to drift the conversation from the key topic of today. I think that what I'm going to present is an opportunity to understand better what an optimization, a multi-objective optimization can deliver. Marcus, I believe that I don't have the permissions to share. I believe maybe you should
yes, I will try to
set them.
see. Let's see.
So in the October release of HEEDS, we are preparing a new technology that accelerates the execution of design explorations, in particular single, multi, and many objective optimizations. That's why I think it's very relevant for the talk of today, because it's usually a time-intensive or computational intensive task to do a multi-objective or a many-objective one. Thank you, Marcus. If we can have a technology that helps us to gain or to get these results faster, then it would be great. So I will take only a few more minutes of your time. I know that we are way beyond the scheduled time for this, but I'm glad that some of you can stay with us. So I hope you can see my my screen. This is part of a more comprehensive presentation that you will get and will be distributed after the release, but I'm giving you a peek preview. So the technology that we are about to launch is called the HEEDS AI Accelerator. This technology is a technology that addresses a very specific challenge in multidisciplinary analysis and optimization. The fact that we often have a simulation time which is very long running for some simulation, CAE simulations, the fact that we have a pressure to save time, like Johnny was mentioning, and also that we need good and robust designs that can help us make the right decision. We don't want only the optimal, but we want a good optimal configuration. This takes time also. And also that we have a lot of data that probably we can reuse to accelerate. So what is the AI Accelerator? Is a technology that is based on artificial intelligence and that provides an acceleration for design space exploration studies by means of knowledge-based, confidence-aware and decision models and decision support. What does it mean? I will get to this in a second. So fundamentally, what the HEEDS AI Accelerator can do is that the final effect, the benefit that it gives is that it saves computational time. It is not making the simulations shorter, or it's not using surrogate models. It is really an AI model, which is a different type of object, because it learns from the calculations that are being done and from the problem at hand in a very specific way. And it saves up to 40% calculation time on average. To give an order of magnitude, it means that what you can do in 10 days, now you can do in 6. So either you have a fixed optimization budget, that means, okay, I have 300 evaluations because this is what I can afford to do. Then this means that these 300 evaluations will be executed in a much shorter time frame. Or maybe I have a fixed optimization time, like Johnny was mentioning, I have a month or a week. And in that case, I can do more calculations, more simulations in the same amount of time. So this technology is able to replace expensive simulations like fluidodynamics or heavy structural calculations or thermal calculations, etc., with an AI model that is learning and directly integrating with your simulation process. This gives a substantial advantage in terms of computational time. So this is an example of an aerodynamic case, which is very simple, but it's still like a CFD one where you need to run and solve a number of cases. In this context, what you see here is that you have this learning process that I'll stop the animation. You have here then the green line. This is the green line, means how many times the AI model has supported the calculations. At the beginning, this is 0 because the AI model is learning. So in this phase, it is learning, and after a certain amount, then it's starting to integrate, to kick in, let's say, and starting to accelerate. So this means that by the end of the computation, you will see that you may have saved in a multi-objective optimization, similar to the one that was presented earlier today, but a more aerodynamic case, I will say. You can save up to 45% of the compute time by the end of optimization. This was 800 evaluations, but already by design to 40, you can save 30% of the computational time. What does it mean? It means that you can save 3 out of 10 days in terms of calculations. So either you can do more and get faster and get more evaluations, or you can finish early and do extra work or extra evaluations that are more specific to the case that you need. This is fully integrated in HEEDS. It works with Sherpa and multi-objective Sherpa, and it's fully integrated. You don't need to be an expert of AI. There is no need to know anything about what is happening behind the scenes, because like Sherpa, this AI accelerator is a self-learning accelerator that helps to get your knowledge at work for you. You gain a lot because this helps to boost your evaluations. We have done this also on very serious and complex cases. In this case, for example, we have a turbine blade palette, a turbine blade that needs to be optimized for temperature. So we want to have a good trade-off between the temperature of the blade and the cooling inlet mass flow. So here the peak temperature should be as low as possible, and the cooling mass flow rate should also be minimized. These two things are conflicting, but we want to make sure that we can optimize the serpentine that is going through the cooling channels to minimize these objectives. This is what is being achieved. You can get these long-running calculations in terms of a saving of 38% of compute time. What it means in terms of day, it means that if you run these CFD simulations, if you run a single CFD simulation on 160 CFD cores, it costs 1 hour and 30 minutes. If you run this for 800 designs, you can save a total of 19 days on the overall calculation. So this is a substantial amount because it gives you really extra time to do more work, more evaluations on this design. So just to give you an idea, normally this type of calculation, if you would like to run it for 800 designs, costs about 50 days. Instead of 50 days, you can save 19 of these 50 days to do other work. So that's a little bit what I wanted to share with you today. It's a capability that will come soon. It works with any simulation tool. It's not only Siemens tools, but it works with any simulation tool that is long running. When it is not particularly helpful is when you run simulations that are very quick. So if it runs in a couple of minutes or a few seconds, it does not make much sense. But if you have if it runs for more than 20 minutes, I will say, then it's definitely giving you a benefit. Okay, I think I stole already too much time of your webinar, Marcus. Thanks a lot for giving me the opportunity to join you and to share a bit of what's coming up in the release.
Yeah, exciting features. Thank you very much. All right, I just want to thank you to everybody for attending this the webinar. And if you have any questions after the meeting, please feel free to reach out to us afterwards with follow-up questions. All right, then I will wish you a nice day. All right, thank you.
Thank you, Marcus.
Thank you.
Thank you, everyone. Bye, everyone.